Hello everybody, and welcome to this presentation about additive manufacturing 3D printing. What could it be used for? We could use 3D printing for ideation, prototyping, consumer testing, but also today for mass production and custom design. Let's take a look at a few of those aspects. What you see here is a study of a vessel, just a proportional look. And in Shaper 3D I can model it, but I can't touch it. So for ideation purpose, before I really go into details, it's actually a very good idea to print out a representational 3D model that's very fast, rough, but I can touch it and verify if I like the design, and then I can go back and further refine my design. This is like a very low resolution print, but very fast. Obviously, 3D printing I can also use for prototyping. For example, designing a face shield. Because 3D printing can be done at home, it's very accessible and very fast, and as a designer I can very quickly run through various ideas and produce them. For consumer testing, then the frames, as you see here, I actually brought to the local grocery store, and then we tested them to see if my ideas or assumptions were correct, where the consumers had concerns or discomfort, and then I was able to take that input and further refine the frames. Additive manufacturing can also be used for mass production, particularly in today's time. On the left side you see an image from a rocket engine. With the 3D printing technologies we have today, we can actually produce constructions which were not possible with previous manufacturing techniques. And on the right side, that is true, it's a 3D printed house. Very low cost, very fast, and on the spot the house can be produced, which makes actually 3D printing for architecture a very interesting topic. 3D printing can also be used for custom designs or one of a kind. I picked here two images, shows you a cast and a prosthetic. Particular in the medical field where you need to make custom pieces, 3D printing is very, very useful. I have more images I could show. So for example, also 3D printing for, since we're all in a pandemic right now, to explore and design face masks. For the hospitals, it was a blessing actually to be able to design and then on the spot locally produce a massive amount of helpers, for example like in this case, to open a door without touching it. Instead of sending it overseas to factories, places were able to produce those right here. This is an image showing you how a scan from a skull can then be used to create a new implant for the medical field. Or here in this case, like a reconstruction of a jawbone. Here you can see the reconstruction of the shell of a turtle on the beak of a bird. Again, these are like those one-of-a-kinds where 3D printing, because we can produce those with the machines we have right in the studio, is very, very cost-effective, unlike traditional mass production techniques. And some further images about prosthetic design, which can go from functional, actually also to pretty nice and stylish designs. Another very interesting aspect of additive manufacturing is also generative design. On the left side you see a traditional seat construction, a bracket, which is made out of multiple parts. It takes time, it's cost effective, but it's complicated. On the right side you see a refined version. It's just one piece that got 3D printed, and it looks kind of very organic because a mathematical formula that is based on bone growth tried to figure out how to design and structure this piece so it has the same durability but is lighter. The right model, for example, cannot be mass produced via traditional techniques anymore. Here we just have to use metal 3D printing. And this is just an overview of, for example, all the different solutions that software developed. This type of generative design can also be used for transportation design. Here again, this is not something that we could produce at a factory. We just didn't use additive manufacturing. And the same can be applied to furniture design. that is the rocket part we saw already. We have printers of all sizes. We can do small pieces, but as you can see, we can also print really, really large. And this is a really great story I heard about a dad who, with 3D printers, printed actually the body of a sports car for his kid. That was pretty amazing to read about. 3D printing can also be very interesting when applied with furniture design. I teach a furniture design course, and this is actually also one of my interested and research areas, because it allows me to combine materials in ways I wasn't able to do previously. And it's visually and also structurally very attractive. Like something like this with all the webbing, it's gorgeous. I could not make this by hand so easily. Here is an image again of the architecture house, you can see. And this is a cut through the wall, so you see it's just a 3D printer that squeezes out liquid concrete, layer by layer, and then builds these spaces. And we can even create patterns which would be so complicated to do evenly by hand, and the machine does that for us flawless. 3D printing is also very interesting technology inside fashion, creating new materials via 3D printing. And it is already applied to shoe design for the sole, because now with 3D printing we can create ladder structures which create soles we were not really able to do before, so the softness and bending, etc. is very great with that type of 3D printing. Obviously also for jewelry, now this can be used of any type, either printing and wearing the plastic print, or creating prints which then can be cast or gold plated, or like here a nice very thin woven structure which probably could do by hand, but this would be extremely time consuming and challenging. So it's a very great addition to jewelry making. And of course we can also use 3D printing to make chocolate and candies. Now let's take a quick look at the different options we currently have for 3D printing, because 3D printing is not 3D printing. We have, for example, FDM, or fused deposit modeling. And this is what most people are aware of. So I have a 3D printer that squeezes out a plastic, for example, PLA or ABS are very popular, and then layer by layer the layers are glued or melted together, and then it creates the 3D structure for me. With FDM printers, I also have a very nice set of various materials. So for example, PLA, and that is infused with wood particles to make this more look like wood. Or I can also 3D print flexible materials, like here, those wheels. It's really great. We also have SLA, so stereolithography apparatus. And essentially what this does is, while with FDM you can see the object is printed from the base upwards, with SLA I pull the piece out of a liquid polymer bath. So layer by layer the polymer will be photoreactive hardened and then creates my design. It's actually a really nice printing technology. For more demanding tasks, then we can use SLS, selective laser sintering. As you can see here, the fidelity is really, really great. And the biggest difference now, if you want to compare those, so FDM is very fast and cheap, but similar to SLA, I need to have supports or specific orientations. FDM is also in terms of resolution, the print that has the least resolution but is fast. And then SLA is somewhere in between. And you can see on the figure, it looks nice and smooth. The layers are much finer, and with selective laser sintering, this is actually the printing technology that does not need any support. As you can see, the object is printed inside surrounding powder, because the laser hardens the powder where it needs and then grows the part inside the powder pool. And then if you take a look at here, we can create very intricate even designs where a piece is inside a piece. With SLS, I also have a choice, for example, to print with metal or other materials, which I do not have with SLA, since this is only liquid plastic. And with FDM, it's also more or less plastic or plastic-like materials. And that pretty much sums up a quick overview about FDM, SLA, SLS. FDM is also the most price-wise affordable one, and SLS is the most expensive one. When you want to have access to various printing technologies, however, you don't have to buy everything yourself. We could go simply to sites like shapevase.com, and those services offer various materials. You can see here we can actually get later a copper, platinum, gold, silver, bronze, or brass piece. So they make a plastic print and then or a wax print, and then they cast it. We can also print something in steel or various plastics. So I, for example, as a designer, could use my very affordable PLA printer at home to do my prototyping, and then when I want to have a more refined print, then I could go to services like Shapevase, select the particular material, get a quote, and then print it. The nice thing about this is I have access to various materials without having to own all these printers. For this video, we will focus on FDM, fused deposit modeling, because FDM 3D printers are the most easily accessible. But everything what we will cover here will also apply to SLA and to a certain degree also to SLS 3D printing. So with my 3D printer, there are a few key elements I really need to be very aware of before I start designing and 3D printing. So the print material is very important because it influences the stability. With print material, with fused deposit modeling, as you know, we can select, for example, between something that's flexible, or I could use PLA or ABS. PLA and ABS are both harder plastics, but ABS is much stronger than PLA, but ABS also can shrink more while printing, which is actually the reason why PLA is the most popular 3D printing material. The nozzle size, print orientation, and also the support I might have to add are influencing the surface quality. The bigger the nozzle or the smaller the nozzle, the more or less layers I have. The print time, the wider the nozzle is or the smaller the nozzle is, the print time adjusts. And all this actually will influence also the usability. Can I print very fine details? Then my print will, for example, when I have a threading, work well. If my print resolution is more coarse, then maybe fine mechanics might not work. I have prepared a set of STL files which I will load into KURA, and then I will demonstrate to you how we're setting up our prints in KURA for general 3D printing. We're now in KURA. As you can see, I work with the LulzBot edition. I like the LulzBot edition because I can have access to the TAS 6 printer. The TAS 6 for me as an industrial designer is a very good working platform because it allows me to use a standard extruder, a dual extruder, and a Moore extruder. So these are completely interchangeable printing heads. The Moore extruder is very big, so I can print 1.2 millimeters wide with 0.9 millimeter high layers. So the prints are rather coarse but fast. The dual extruder is really nice when I would like to print with PLA for the object and water dissolvable material for the support, so I could wash it away. Very good when I want to print a piece inside a piece. And the standard extruder is just a small nozzle, very good for fine details, but obviously that also means longer print time. So what we will focus on first is how we select the print material, how we specify the nozzle size and the layer height, and what all this will mean for our print. So we'll start with the TAS 6 standard extruder. I have very good experience with printing with PLA. PLA sticks better to the printing surface compared to ABS, and I will use the high detail. I will load a test file I prepared. There it is. It's just a threading, half of a cap, so I can see actually the threading cut through. And lower right corner here, you will see in KURA, it tells me now the print time, 1 hour and 38 minutes. So what does this mean? Let's go to the layer view. And there we see now these red lines. These are the layers. I have 165 layers, and I can go up and down, and it basically shows me how this object will be printed. Very good. Let's go to high speed. The software will slice the model. Takes a second. So now we are down to 49 minutes. We only have 79 layers. So we can see actually from here already the layer is much better. And the print is faster, but it is less detailed. I will zoom to here and pay attention to how we can see the gray outline of my threading, and the printing layers are not necessarily perfectly following it. I will switch one time back to high detail. And there you see now it captures the shape much finer. But it also takes longer. Now let's make a switch over to the Moore extruder. And I will not use the high speed. Yeah, I will use the high speed, not the high detail. I will turn the support off. And the print is now 10 minutes, so very fast. We went down from 1 hour and 40 minutes to something like 10 minutes. But you can see the quality of the print is actually not really that great. But this is good to be aware of, because if I don't need the precision, then I can use a more coarser or faster printing head and get my test piece done sooner. And then if I need more quality, then I can switch to a more refined print. Let's take a look at how actually these prints also turn out. I have here one print that is done with the standard extruder, very high quality. The standard extruder in a coarser quality, so we have less layers, so thicker layers. Then we have the Moore extruder with high speed, and the Moore extruder with fine detail, and the Moore extruder with coarse details, so fast print. So if I take these two and rotate them, and then we can compare actually the threading, you can clearly see how with the fine detail, sharp edges and the threading is really well captured, while with the Moore extruder it looks very round. But again, this is 1 hour and 40 minutes. This is 10 minutes to print. Now you can also see from here how, for example, the threading with the fine detail is captured better, and the threading with the fast print and the bigger nozzle is not captured that much. And that basically is very important to understand when you want to print detailed parts. And while I showed you just an example with a threading, this is very common essentially for all 3D prints in all types of shapes. If you want obviously to do a mechanical test, here I have a shell which I printed with fine quality, and here I have my head with a fine quality, and I want to figure out if this really works. Then obviously I need to print those in a really good quality, so that when I prototype everything, it will work. So you see the layer height and also the nozzle width really influence the print quality and then the time. Let's take a look at the support and the rotation of a print. That's actually very important to understand. I created 3 prints of this object. Vertical one way, vertical the other way, and one print was also done horizontal. I would like to talk about the differences here, the problems, and how we can set this up in KURA. So I would like to print this cap, which is basically part of a water bottle. And I would like to prototype it. So that means I would like to have a vessel where I can put this one in and the threading should work. And this is a really great exercise to also show you how mindful you have to be with the rotation and the support at the same time. So when I rotate this one, you can see that the print layers are horizontal. This piece was printed horizontal. But it creates a problem with the threading. As you can see, the threading on top is stepped. And I put a support on the bottom. In this case here, the support is already removed. And there you can clearly see where the support touched the 3D print. This is also the Moore extruder, so it's very coarse, meaning also the support left over is stronger pronounced, which actually makes it visually better to see. So this type of print was not necessarily very good. I did also one print this way, because I wanted to have kind of like a more horizontal layer. But when I print this piece in this orientation, you see I need to put support inside the opening. And I will go into this detail very soon. And it also put support actually along the threading. Now I have to remove that support, and because there is support on the threading, my fear is that the support kind of like made the threading a little bit dirty. Which means when I remove the threading, the support, the threading is not running very smooth. And here in this case, I simply printed it upside down. For me, the quality of the handle is really not that important. The threading is important. So I position it this way. And as you can see, the threading is completely clean. There's no support on it. The rest is all engulfed in support structure. And this, with a plier, I could go ahead now and break away. Very good. So let's take a look at KURA and how we can rotate objects and how we can do the support. To rotate an object, we can select it, and then we simply go to rotate, and then we have here these axes. So to put this upside down, I can rotate it along the x-axis or y by 180 degrees. Very good, very easy. When I look a little bit from below, you see all these red lines, red surfaces. And that is a visual indicator that there is an overhang. So what does overhang mean? Let's take a look from here. When we would print, the machine can put layer by layer the plastic on it. Let's take a look at the layer system that illustrates it really well. There. So it puts it layer by layer on it, and then it has to horizontally expand. But there's nothing below to hold the material, and because of gravity, it would simply fall down. I have a set of test images of letters that show the geometrical problems and how we fix them. I will show those in a moment too. Now, to create the support, which we need, we can go to Generate Support. And the software now will figure out, based on the nozzle and the printing layer and the overall geometry, to what degree it has to add the support. You also notice this switch now to 59 minutes, and before it was just around 31 minutes. Let's go back to support one more time. There we are. Very nice. Under support, we also have something called build plate adhesion. Currently it's set to skirt. These two lines is a skirt. We can also set this to none. I will turn support off for the moment so it's easier to see. And this piece will be printed at the small layer onto this platform, and chances are very high at one point it will get loose and then the print will be failed. So we need to make sure that this print has a bigger base. Think about this way as the build plate adhesion. So we can, for example, add a skirt, but the skirt, as you will see, only actually goes around. Helps a little bit to increase the flow of the plastic inside the nozzle before the printing really starts. In this case, I could add a brim. Think about a brim more like something like the skirt, just bigger and is attached to the print. And then this actually will help to create a bigger suction to the platform. And you see then when I create the support in this case here, this is a much bigger platform and the brim goes around. So in this case, I don't really need the brim at all. So I could remove it. Very good. So talking about the support. It's nice and white. I could go now to Custom, go to Support, and take a look at what I have here. There are various ways I could, for example, do the support. Maybe let's use lines. We're also at 59 minutes. So lines actually add a little bit more of printing time. But it's also a different structure. What about grid? Maybe we actually go to a cut section. There now we can see how this is gridded. So it's a nice strong support. Where you see the time went a little bit up, and with zigzag the time went down, and we still had a good support. So this is actually fine. Very good. The support in the KURA has one interesting additional option. I can go to Experimental and turn on Conical Support. And what Conical Support does, you will see just in a minute, it will minimize the starting point of the support, and then where it needs to hold the part, it will expand. So we're down to 48 minutes. If I turn this off one more time, we're at 59. So we saved 11 minutes. Might not sound much, but think about you have to print this piece 6 times, then you're saving actually an hour already of work time. Very good. Here's a test case, THYYO. This is a very good example to show the various geometry problems you need to be aware of when you do support and build plate adhesion. So the T and H, they have horizontal parts, so they need to be supported. We have the Y with a 45 degree and it needs support. The Y where the angle is less strong doesn't need support. And then we have the O that needs support at the base as well as inside. And for build plate adhesion, I set skirt and not the brim. Okay, so the reason why this is also very interesting to do is there can be variations between if you print with a coarse printer or if you print with a fine printing head. So the support you see might sometimes be just a suggestion. So let's take a look at what this means. We will start with the T. Bring this in. There's the T with the support. Looks very good. And here is the T without the support. And the top both look very good, but when I rotate it, there you can see how the plastic had no support to sit on and it just moved down. And over time the printer was able to put enough plastic down horizontally to make sure the top worked well. When we started looking at the support, I also made a connection to the build plate adhesion. You see we have 1, 2, 3 contact points for this T, so it's nice and broad. Here we have the brim, that's also nice and big, and here is a print where I used just a skirt, so only the T was on the print plate and it got loose, and then there you can see at one point the printing piece moved and the printer just put out the material. That is the reason why sometimes you can get away with a skirt when you have sufficient amount of support around your object, or your object has a big base. But like with this T, when you have a small base and no support, then you need to have a brim. Very good. Let's take a look at the H. Here's the H without the support, and below there you can see it hangs down just a little bit. And here's the H. I removed the support, and when we compare, there you can see that the lower edge is actually a little bit straighter because it was printed right on it. Let's take a look at the Y. The Y is actually very interesting. So the 45 degree with the support as needed. But interestingly, with a different printing head, it didn't need the support. And you see, it even worked. Now I also have, for example, the same shape printed with the big printing head, the Mora extruder. And there you can see that the top kind of like got destroyed. The plastic moved a little bit. This is just due to the slicer and the printing head. And this is why I said whatever you see in KURA, take it with a grain of salt, make test prints to be sure you're not coming across some print accidents. And here we also have the O without the inner support. You can see how the top is actually more flat. And here we have the O with the support inside. That then helps to make the O a little bit bigger. One tip for rings, or in particular when they're smaller, you can also use a drill and then clean drill those cylindrical shapes to be perfectly round. Well, we will go into how to print holes today too. Let's take a deeper look at the build plate adhesion and also the orientation one more time. I have here an end cap, and as you can see, the bottom part is red, which means it's an overhang, and the software will suggest that we need to have some sort of support. And there are various ways how I could print this object. So if I would print it this way, the object that would turn out this way. Nice and round. I don't have any support, but you can see that the rounded edge did not really get captured very well. Also, this is flat, and here I have a sharp edge that's actually called elephant foot. The first piece there, the printer tries to squeeze out a little bit more plastic to stick better to the surface. So to print this better, I know I can rotate this by 180 degrees. Then I will have a horizontal array here. And I know at this point I need to add support, obviously, because otherwise the print would be failed. So there's the interior support. And then this would turn out like this. So there's the support that's inside. But this detail, if it's for me important to print well, was captured really good. Let's compare. This is the print orientation. And there you can see the outcome. But also the left one is faster. The right one is slower because of the added support. But the right one simply looks better. Also, everything was printed horizontally, so I have nice horizontal lines for these rounded edges. Okay. Let's rotate this one back onto the ground, because there are other variations. I on purpose show this cut model because now we can really nicely see when we add a skirt, for example, where it will be placed around. There's the skirt and a little bit of support. If we then add the brim, it gets closer onto the model. And one technique sometimes is, if I have particular details, I just create a raft. The raft, think about it as a platform, like a grid platform, so I can minimize elephant foot issue, because the first bigger squeezed out material is actually the raft. And the raft then printed looks like this. And then I simply, with my finger or plier, break this off. I have the raft also under half a print, just to show you a variation. You see here we have the interior support. At the bottom we have the support and then the raft. And when I remove it, again, this is printed with the Mora extruder, so the support is a little bit bigger. When you can see, the side needs some serious cleanup work. So this is not a very good way to print. Let's take a look at how we can print big pieces also really fast. Particularly the Mora extruder has a very interesting feature that's called spiral vase, and it's 40 minutes long. And when I go to the layer, then there you can see it does not print everything inside, it's just a thin surface. This is actually really nice when I want to make a very quick print. Here I'm holding it into the camera. It's just hollow, and it's just very good when I just want to touch it. It's very good for cylindrical shapes. If you do not have this printing at and we want to print something like this, obviously we're not going to print such a big piece with solid material. So let's go to high speed, and then we can take a look at what infill actually means. So the software is sliced, and we can go up and down, and you see when we go down, we see a yellow material inside. So let's zoom in a little bit. So red is actually the outside wall, so the shell. And green is an inner wall, and then the yellow here, that is actually the infill. So 15% infill. Maybe let's set this to 60, and you can see what happens. There now we have a much finer infill. The reason why this infill is very useful is, first, it stiffens up the interior space, so I can't collapse it. And like here in this case, when I want to print a solid piece, I also need interior support for the top to be printed. And that essentially is what the infill will allow me to do. Sometimes I have to adjust the numbers for infill to make sure on very big horizontal surfaces it is nice and smooth and not having issues with the plastic falling down. The infill can also be customized. So when we go to custom and infill, similar to support, also here I have various patterns I can select. And then those will generate various structures. From my point of view, very often I go with the default values. I found them, to be honest, in 99% cases, always working actually really well. Also here with the infill, we have 1 hour and 43 minutes, 20%. Let's go to 50%. This is now 2 hours and 49 minutes. So it's significantly longer. The only question is, I use more material and is it more stable? So the sweet spot here is trying to figure out what is the least amount of infill you can get away with. So it's faster and cheaper. Let's actually open OneCap, because also there you see the infill always at work. There we have it. So if here the object is actually very small, I don't really need a very high infill. For the vessel maybe, or if I press hard on it, I might need a little bit more infill. But here with something that is rather small, I can definitely get away with a smaller set of infill, and that will be then strong enough. Let's take a look at wall thickness in general. So far we covered support, infill, etc., the orientation, material, and the next one that is very important to be aware of is wall thickness. So I have various test walls here from 0.5 to bigger thicknesses. And I use a motor extruder. It has a 1.2 millimeter wide printing head attached. So let's see how I can print this. And you can see the first and second and even the back wall cannot be printed. So the nozzle is too big for this fine detail. If I switch now to the standard extruder, it works better. Now when we zoom in here, you can really see this 1 millimeter is printed, but the 0.5 millimeter wall is not printed at all. So it's too thin. Basically this means your wall thickness has to be, at least with fine printing heads, double the width of a printing nozzle. Let's make a switch to Shaper 3D, because I would like to continue talking about the wall thickness. Here we have the original vessel as a solid. That's the one I sent over to KURA to do my vase print. And now I would like to prepare this for prototyping, and I would like to use the motor extruder, which is 1.2 millimeter wide. So I know that, and I said ideally have a wall thickness of 2 paths. So 1.2 millimeter width multiplied by 2.4 millimeters. So that means when I select this face and I go to shell, ideally here I want to put in a number that is n amount of an n amount of the width of the nozzle. It does not always have to be twice, it can also be 3 times or 4 times if you want to make it thicker, but it's more plastic you use and it takes longer. So let's go to the front view and turn on cut section. There you can see how nicely we see actually the surface being shelled. Now let's take a look at KURA. Here I have a further refined piece put in, and now we can go ahead and start setting everything up. So we know we want this to be rotated by 90 degrees. Very good. That is fine. Because I want to print in halves. This is also one trick. If sometimes printing it in one piece is too complicated, just print in halves. We are using here the more extruder. I have high speed set up, very good. Print support is on. And let's take a look at the layer view. Then I zoom in a little bit and this looks pretty fine. I can switch to the task 6. And you can see how the same model, just with a different printing head, will look. So it took already a little bit longer. There we can see we have interior and exterior walls, so 4 paths. So for the task 6, for example, here the walls are actually a tick too thick. I could at least remove 1 layer if I want to. There's another case I would like to point out also. When printing wall thicknesses, when for example they are not exactly the same or not the correct n amount. So I will go back to the more extruder and I will rotate my object back to 0. Yeah, very good. Because I would like to take a look at this upper part while it looks like a cylinder. Go to layer view, very good. So, and let's zoom in. So we see 2 paths here. If you're new to this, you might however overlook what's happening here. So you see there's a thicker inner and then there's a thinner outer and it has some dots on it. So that's a visual indicator that the wall thickness here is actually not 2.4 millimeter for the more extruder. So this I can print. The print quality, however, will not be very good. I can also go to custom. Now let's take a look at shell. There it tells me wall thickness 2.4, wall count 2. So this is not really the correct amount. When I am inside Shaper, to adjust later a print to the correct size, I will go to my other folder. Here I have a design. Actually here let's use finished design. There we are. So there you can see there's a vessel including the threading. Now I can select any surface here. So 2.8 is the inner radius. In this case 30 is the outer radius, so 2 millimeters. So I'm short of 0.4, which means this should be 27.6 millimeters. And then the software will update it for me. You see, super good. And everything there was done on the fly. There you see how growing and shrinking did it. Very good. So you don't have to necessarily model everything already correctly. You can just model in one way and then you can adjust everything for your 3D printer. So then this way, if I want to send something later out to like a fine print in SLS, then I can adjust everything to the values I really only need. And that's a great direct modeling capability Shaper 3D offers us. Let's continue talking more about the wall thickness, because there are a few more elements which are really useful to be aware of. This also then goes into print stability. I used here this vessel simply as a demo to also show how we could create a web and how we can do add ribs, and also talk about the problem of mating. In the video you can see I have everything nicely printed. I decided here to print the support outside, so I can shave this off and then with a sander, if needed, clean this up, because my important focus was the threading and also the connection parts. So the wall thickness, the holes I did a little bit bigger because I wanted them to snap. Now you can also model everything if you want perfectly flush. In Shaper the pin is nearly exactly as wide as the cylinder, and then after the print is done you simply take a screwdriver and a drill, and then as you see here what I do, you just drill it clean. So what's the advantage of this? The advantage simply is that I can now with a tool make the circle really perfect. In my studio, for example, I would use a drill press. I would not hand drill it because I really want a perfect hole. But then this way you will get really perfectly flush and also tight prints. Now I made this a little bit wider. You see now this is too loose. And here when I drilled the first time, it's still pretty, I don't want to say tight, but it holds it together pretty good. Another thing also to keep in mind is how things can deform. You can see there's a tiny gap, and it's just because the print deformed a little bit. Be aware of that. Again, maybe I could sand this a little bit and make sure the top surfaces are perfectly flush. There would be an issue here with the pins, but maybe here somewhere with sandpaper I could clean this up a little bit. In terms of stability, 3D prints with fused deposit modeling is layered, which means, you can see all the layers. When we have a small object, if I press really hard, I can break this off. So to stiffen up bigger objects or to add stability to small extrusions, we can add a web or add ribs. And I will show how we do this. Before we continue, one thing to keep in mind, you see here, interestingly, also be aware of this can happen. The layers didn't really fuse perfectly together. This actually also happened here, and even there you can see this. So maybe the print I did there with the wall thickness for the fine printing head was actually not matching the N amount. Okay, so let's take a look at Shaper and how we can create this. And it's also a little tip how I would build everything. So these are finished pieces. And I have right next to it the individual elements. And the way how I model is I have my one part, and I have here also like those parts, construction line, and then I select everything, move it to the side, make a copy and fuse it together. So the web is simply helps preventing everything to collapse. It's quite logical. We add this geometry inside and then stiffen it up. Here in this case here, the web connects to the cylinders, so the cylinders are not freestanding. The cylinder is freestanding, and because of the layered way of printing, and the longer it is, higher the chance it might break off. That's the reason why I added those ribs to it. Now to create these ribs is actually very easy. Let me delete this part and run you through the process I did. So I first created a construction line. So add construction axis through cylinder or cone, and then I selected the cylinder, and then it adds that guideline. This is now perfectly centered. Now I will add a construction plane through edge at an angle. Then I select this line, next, and I can specify the rotation. This is the way how I did this. And now with my finger I can double tap onto it. I will turn on cut section view, and then on that plane I drew this triangular shape, my sketch. Also you can see it is slightly inside my shell and my tube. So when I then go ahead and say this extrude maybe 0.5 millimeter one direction, but as in your body, and then do the same there. I have to hide this construction plane for the moment. So this I would like to be 1 millimeter. Very good. And now I can go ahead, double tap it with the 3D widget here, move maybe to the upper edge. You see it's a cylinder, finds the center, make a copy, and start rotating it. So that's the way then how I created those elements. Very easy. I would like to show the other one. It's just the opposite part. There I have the cylinder, and then I extruded a pin. And to make the sliding a little bit better, I chamfered the top part. So to create these ribs is actually very easy. I will go to the front view, and I will turn this on and hide this. There you see I drew these shapes. And this I will hide for the moment so we don't see it. Very good. And I just select this shape here as a single one. Extrude this down. I know I would like this to be perfectly on the surface. So I will go one time back, hide this for the moment, because this I would like to hide too. There. Very good. Oh, I must have not hidden it. Hit the wrong one. There. So then these two I pushed on. Okay. Now check this out. This is actually really great how direct modeling here works. So I zoom in a little bit and try to see the lower surface. And that lower surface I would like to be pushed onto the cylindrical shape. So replace face, select the target, done. There we are. And I can do the same with this one here too. Very good. So you see it's very, very easy, and it's not extruding right into it. It's really, I will delete this one for a moment to show you, it's really matching the curvature. You can see how these pins perfectly sit on it. So then those additions for the support really help actually creating everything and making the prints nice and strong, like you see it there. The pattern I created is also more a guess. I thought I need at least one in the middle line, and maybe here and here one, not more. I kept this one freestanding because I wanted to show those small fins for modeling, and then here the cylinder, I actually connected the web to it to give you like two ideas how we can add these parts together. And again, I printed this one horizontal, so these interior parts were support free, and then because I was, for me, the part I wanted to study, and the outside I could clean up with sandpaper and some patience. Let's take a look at how we can design threading and also customize them for our easy to access 3D printing machines, or perfect them for mass production with finer machines. So I have here my design, and I explored various different threading options and threading types. Let me hide all those objects. Let's zoom in a little bit, and we'll show you how I modeled the threading. So you can see I have here all the lines that define the threading, and I sketched everything so it perfectly sits on each other. To create a threading, I need to select this fill, then I select a revolve axis, then I can go revolve, and now I add an offset. There we are. Very good. So this, if I want to make more, I just copy, move one further and one further. Very good. And then all those, to make it into one, I can join together. Now if I would build the piece that is in between, the threading would be perfectly next to each other. That's not good, because the 3D printing will have some deformities plus issues on the surface, so we want to add a tolerance, a little bit of spiel in between. This is actually very easy. I sketched my layout perfectly on purpose, because now I can select each side and then add a little bit of a surface offset. And you see the whole threading actually was adjusted. So now I added 0.1 millimeter of distance, and I would have to do the same to the other side too. You can create a threading that is very linear, or you can also create a threading, like in this case, that is rather round. So I used here just a spline to create that shape. Let's take a look at the video. There we can see how I put these two pieces together. So that is actually printed with this 0.1 millimeter, so 0.2 millimeter each side, and I have very little amount of spiel or tolerance, and it slides perfectly. Now when you print threadings, you have to be very careful about also your detail. So I have here one print where I use rather bigger layers, and you can see how the threading is rather stepped vertically, and here is a print with fine layers, and if you compare those, you can really see that they look close, but the left one simply is better. But you can also make big threadings. You don't necessarily only have to make fine threadings. Particularly for initial prototyping, if you want to rotate something, make it big, it's easier to print, it's easier to use. We can always change those afterwards. Remember, like in my design, the threading was an individual object, which later I fused to the bottle. And also as a tip for test pieces, so I wanted to figure out if my threading is good. You see, I only printed a piece of my cap and a piece of my bottle. Why should I print everything completely? And now when I put this together, I know that with the printing machine I have right now, this threading actually works out really good. I could maybe even try to get it a tick tighter, but if I continue rotating it, it seals perfectly.